very warm welcome to today's Cell and Gene Therapy Insights webinar, titled Key Considerations for Shortening CAR-T Manufacturing Process. I'm Lauren Coyle, an editor at BioInsights, and joining me today is Nadine Mockel-Tinbrook, who will discuss how a one-week automated CAR-T cell manufacturing process on the Clinimax Prodigy platform enhances production, reduces cost, and produces potent CAR-T cells for treating relapsed or refractory B-cell malignancies. After the presentation, we'll have a live Q&A session. Now, I'd like to introduce our presenter. Nadine Mockel-Tinbrook leads CAR-T cell process engineering and non-clinical development at Miltenyi Biotec, focusing on automated CAR-T cell production for clinical trials and immunotherapy. So without further ado, I'll hand over to Nadine to kick us off with the first presentation.
A warm welcome to today's webinar. My name is Nadine Mockel-Tinbrook. The topic is key considerations for shortening your CAR-T cell manufacturing process. The platform which we are using is the Clinimax Prodigy. It comes with a certain flexibility as there are several proven applications available of which you can choose. It also has parameters which can be changed to serve your procedures. As it's a closed system, it will reduce cleanroom size, and it comes with automation, which will reduce the costs for your staff. The good thing is just one device which you can use from discovery to commercial scale. And as it's already a clinical proven system, you can minimize your time to market. And it also enables upscaling your manufacturing area. The good thing of the Prodigy platform is as it's automated, you have standardized and reproducible procedures, which brings a certain consistency to your product quality. It's a closed system, and thereby you can reduce the risk of contaminations. And the good thing is you have automated logs and protocols. And we at Miltenyi enables reliable supply, full service, and regulatory support. The application which I'm talking today on is the Clinimax Prodigy T-cell transduction. On the left side, you see a classical scheme of a CAR T-cell manufacturing on the Prodigy. You can start with fresh or frozen material and then perform on day 0 a cell selection, for example, CD4, CD8 T cells. Those cells were activated with Transact, and 24 hours after activation, T cells can be transduced, for example, using GMP lentiviral vectors. After transduction, there is a culture phase, which will end after 12 days, at which the cells can be harvested, and, for example, the drug product can be formulated and filled using the Clinimax formulation solution. On the right side, you see a classical activity matrix, so the feeding schedule of your T cells or CAR T cells in the process. The Prodigy comes with pre-programmed protocols, like a standard protocol, an enhanced feeding protocol, which is depicted below. But you also have some protocols available with spin oculation in case you choose to use a retroviral vector. And for your convenience, there's also an empty matrix to flexibly build in your protocol. So how does it look like? You see here the guided user interface, which is on the Prodigy. And there you have the possibility to add or delete activities. What are activities are available? Classical activities like feeding, its media exchange, but also feeding, culture wash, transduction, and all of the activities can be added or deleted as you need, and they can be defined by date and time for every activity. So the software is flexible and can be adapted to your specific needs. For example, for shortening the expansion phase. Why should we shortening the expansion phase and thereby your manufacturing process? So cells are less differentiated and might come with a better in vivo expansion and persistence of your final product. You will reduce your vein-to-vein time when working with fresh material. And, for example, if patients are in a critical situation, you ensure a faster access of this drug product. You also will use your resources more efficient, meaning shortening the manufacturing length will reduce the occupancy of your individual devices, and thereby you will also reduce the costs of your manufacturing processes. Implementing flexible harvest time points will enable you to better plan and utilize of your existing resources, and unexpected events or holidays can be bridged by more flexible process lengths. And finally, you will have a greater production capacity. With the same infrastructure, you can manufacture more products within the same or even shorter time. So how can you shorten your manufacturing process? Again, you see the classical scheduling of a CAR T-cell manufacturing on the left, and shortening your expansion phase. For example, harvesting the cells after 7 or 10 days will shortening your whole manufacturing process. On the right, there is an example given for activity matrix at which you either harvested your cells after 7 days, 8 or 10 days. Important to mention is that we have implemented 2 cycles of culture wash early in the process. The reason is to increase your wash intensity early on, so that you can lower the vector burden on your process, on your final product, which you might already harvest after 7 days. So what did we do here at Miltenyi to characterize the processes with shorter manufacturing time? So first of all, we start with frozen starting material, as this will also increase your operational facilitation. And then we perform the classical schedule, doing T-cell selection, activation, and transduction. Here we choose either for CAR1 or CAR2. And finally, we expand the days until day 7 or 8 or 10 and 12. To characterize the processes, we take in-process controls even at different time points and analyze by flow cytometry for cell count, cell viability, cellular composition. We analyze the transduction efficiency and calculated the count of total CAR T cells. And additionally, we also checked for vector copy number. Important to mention is that we supplemented our culture media with recombinant cytokines, IL-7 and IL-15, and constantly use human AB serums throughout the whole process. So we come now to the results of the process characterization, and what you see here is the culture performance. So how many cells do we manufacture within the different time points, and what is the viability of these cells? On the left side, you see the results for the runs at which we use CAR1, and on the right side, you see the results for CAR2. Overall, we see for all of the runs comparable growth curves, and we see a reproducible manufacturing independent of the process length, meaning on all products we have manufactured, we have a quite high viability above 98%, and we were already able to manufacture 2.5 billion T cells within 1 week. So this scheduling gives you the flexibility to stop your process when sufficient cell numbers are available. Next step was to check for cellular composition, meaning what is the frequency of T cells, CD4, CD8 T cells, monocyte B cells, but also NKT cells, granulocytes or B cells. On the left, it's depicted for CAR1, on the right for CAR2. And what you see is that you, by already enriching T cells, you're reducing the contamination with non-T cells early in the process. But of more interest is how does the product look like? And if you harvest it on day 7, 8, or 10, or even on day 12, you see no differences in the cellular composition. You have mainly T cells in your product with frequencies higher, 98, 97%. And what's also quite interesting is that independent of the CAR, you have a comparable CD4 to CD8 ratio, which is mainly driven by the donor you used. As we are talking today about CAR T-cell manufacturing, it's also quite interesting to check for CAR T-cell expression. So here you see the results for the frequency of the CAR used and the number of total CAR T-cells throughout the different processes. And what you can see is that we have a quite high number of CAR T-cells with around about 1 billion already after 1 week manufacturing. And you also can see that we have a stable integration of the lentiviral vectors earliest after 3 to 4 days after the transduction was performed. One important thing to mention is that early IPC, for example, on day 3, by flow analysis might be challenging. You see it, for example, on the right side for CAR2 on day 3. You don't have that distinguished population, and the frequency with 17% is lower than when the CAR is stable integrated. And here we have a frequency of 29% for this donor. Meaning, in case you have to do early IPC, you might switch to an qualitative instead of a quantitative measurement or use different methods like qPCR. But in general, shortening the manufacturing, for example, to 7 days, enables you to manufacture already up to 1 billion CAR T cells within 1 week. Besides process characterization, we also perform product characterization of the different manufacturing processes with different time point of harvest. So what we did was we harvested the cells again after 7, 8, 10, or 12 days, formulate them in Clinimax formulation solution, and then store for up to 96 hours at state 2 to 8 degrees. And then we analyze by flow cytometry the shelf life, so the cell viability over the storage time. And for the fresh product, we also analyze the functionality, either by in vitro methods, like cytolytic activity or cytokine secretion, or we also did an in vivo long-term efficacy study comparing 7 to 12 days manufacturing. So first of all, you see the shelf life of CAR T-cell products depicted here. When storing up to 96, or in case of CAR2, 72 hours, we see no impact of the process length on the shelf life of the product. So cells harvested after 7, 8, or 10 days for CAR1, or 7 or 12 days for CAR2 do have sufficient viability above 80% during storage. So the process length and the time point of harvest do not negatively affect the shelf life of the CAR T cell. One important tool here to mention is that we use constantly human AB serum throughout the whole expansion phase, which have a positive effect on the shelf life of the fresh product. So next step was to check on functionality of the cytolytic activity or the cytokine response upon co-culture with target cell lines. In case you want to have more information about the method used, you can refer to the application note, maximize the efficacy of CAR T-cell functionality assessment via flow cytometry. So what we did here is we harvested these cells and put them in co-culture with either RAT T cells for CAR1 or with JAK1 target cells for CAR2, and analyze, depicted on the left, the cytolytic activity. And what you see, independent of the process length, the CAR T cells were capable to kill the target cells in an effector to target cell dependent manner. At the same time, these CAR T cells were capable of producing cytokines. So we analyze this in the supernatant of the co-culture and check for, depicted are here, IL-2, TNF-alpha, and interferon gamma. And interestingly, for CAR1, for example, the differences between 7 or 10 days manufacturing are very minor. So you see nearly no or minor differences in cytokine secretion profile. Whereas for CAR2, at which we use also a different target cell line, we see differences in process length and cytokine response to target cells. This might come with a different differentiation status of the CAR T cells, at which it's in the nature of the T cell that younger T cells produce higher amounts of cytokines. And finally, we compare the in vivo efficacy of CAR T cells derived from different manufacturing lands. Therefore, we choose a classical NSG mice model at which we injected 0.5 million RAG cells 7 days before the therapy was initiated with CAR1 T cells. Here we used 1 million CAR T cells per animal, and then we monitor the behavior of the animals, but also perform IVISH measurement at indicated time points. On the right side, you see the results, either the individual animals, on the top the untreated control, and on the bottom comparing 7 days to 12 days manufacturing. And what you see on the summary plot on the right side is that independent of the manufacturing length, the tumor burden was reduced of the animals, and the animals were tumor-free after 5 to 70 days, and we do not see any differences in the manufacturing length. This brings me already to the summary. So what we did to understand the effect of shortening the CAR T-cell manufacturing process length, we did process characterization, at which we can show that flexible harvest time points enables you to stop your product manufacturing when the dose is reached. We show that we have a reliable and robust number of viable CAR T cells, either if we already stopped after 1 week. We see a stable integration of the lentiviral vectors after 3 to 4 days after transduction, meaning process day 4 to 5, which can be demonstrated by either analysis of the transduction efficiency or vector copy number analysis. In case you have to perform early in-process control, so before process day 3, that might be quite challenging, and this is dependent on the CAR construct which you are using. So in case you need an early in-process control for fresh products, you can consider alternative methods to flow cytometry or switching to a qualitative instead of a quantitative readout. We also analyze the shelf life of products derived from different manufacturing lands, and we see that the shelf life is not affected when the process time is shortened. For all product we had manufactured, we see a sufficient shelf life with viability above 80%, either if we stored them for 96 hours. And finally, we also demonstrate in vitro and in vivo functionality. We do not see any negative effect on the functionality of the CAR T cells when the process time is shortened, and we see comparable in vitro cytolytic activity for the drug products derived from manufacturings with different process lengths. And younger CAR T cells seems to secrete higher levels of cytokines, which is classically associated to less differentiation of these cells. Finally, we also compare in an NSG mice model the in vivo efficacy, and here we also do not see any differences in CAR T performance independent of the manufacturing length. Besides us, there are others using the CAR T manufacturing platform on the Prodigy. There are several partners which are in the preclinical phase using a 7 to 9 days manufacturing schedule. And there are already some, here are 5 publications which are already in the clinical phase. And this comes to an end, and want to thank you for your attention.
Nadine, thank you so much for a great presentation there. We are now going to start a Q&A. And our first question we have here today is, if I want to establish the 7-day process within the framework of clinical study for CAR engineered T cells, what other parameters do I have to consider?
It's not only the manufacturing procedure, so you for sure have to consider your clinical protocol. So that's meaning, for example, if you need a lymphodepletion before treatment, you have to be sure about the window of the lymphodepletion and what's the window on the clinical side. You also have to consider if you have to adapt your QC strategy and build in some suitable timings for the IPC strategy. That's important. And another perspective or a consideration is the logistics. So if you want to work with a fresh product, for example, you have to consider what the distance between the clinic and the manufacturing site if you're working on a decentralized manufacturing strategy. So there are a lot of considerations which you have to take into account before you can build in your manufacturing for a clinical trial.
Fantastic, thank you. Our next question is there a dedicated time point when the samples can be considered as safe in respect to viral vector burden?
So maybe you realized during the presentation that we had adapted the activity matrix accordingly to this question. So there is a need to reduce the viral vector burden on your final product. So we implemented additional washing steps there so that the drug product, so the day of harvest, day 7, that we cannot detect any free vector in the supernatant, but also on the cell bounds. And that is the earliest time point for the application, or the protocol, which we presented here, on which we have a low vector burden, and it seems to be safe at that time point.
Wonderful, thank you. Can I also do a shorter process with a maximum of 2 to 3 days expansion on the Clinimax Prodigy? And what is the advantage of the 7-day process in contrast to the ultra-short process? So
for sure, you can also reduce the expansion time to 2 to 3 days, like Novartis T-Charge process. They're also using the Prodigy platform. So the platform is flexible enough that you can build in shorter manufacturing processes and can modify the activity matrix for activation, transduction, but also required feeding steps. The advantage of the 7 days process, so not being that short, is that you can still work with a fresh product if you intend to or if you like to work with a fresh product. Because there at the time point of harvest, your critical quality attributes or your QC parameter for release of the drug product, and especially the microbiological testings, are available. This is for a very short time that's not working so far.
That was great. Thank you so much. And what is the starting cell number on day 0?
It's 1 times 10 to the 8. So with a classical scale application, we're using 1 times 10 to the 8 selected T cells. There's also an application available, it's called large scale, where you can work with 4 times higher starting numbers.
Fantastic. And does early harvest increase the percentage of cycling cells?
So is the answer is in, right? I already answered that. So that's the idea of early harvest. So to have higher numbers of less differentiated cells, so reducing numbers of differentiated or finally differentiated cells, which then most likely have a better performance in vivo. That's a hypothesis behind. It needs to be proven on a clinical trial.
Fantastic. So we do have a couple minutes left, so we should be able to get a couple more questions. But to our audience, please do keep sending them in, and any that we don't get to today, we will be able to answer by email. So our next one here is, what is your cellular composition test on slide 7?
I think this was answered then later on. It's just the composition of different cell types and unwanted cells like NK cells or B cells. You can easily analyze by flow. That's
fantastic. So we have one here. Some CAR-T and or TREG only use anti-CD3 plus IL-2 for expansion. Can you coat the bowl with anti-CD3?
It's technically possible. So that's for the plastics, the chamber is designed, that's possible, but it's not automated or built in the current TCT application. So what we are using is the Transact reagent, which is also a polyclonal stimulation built on CD3 and CD28. And for IL-2, yes, for sure, you can choose any cytokine you want to work with. It's not only developed for IL-7 and 21. You also can use IL-2.
Fantastic, thank you. And I think we have time for one more. So is the human serum used only in the expansion phase or also during the activation and transduction?
It's in there the whole time. So we added it to the culture medium on the starting day and then using it until the end of the culture. And it's there during activation and transduction.
Amazing. Well, thank you, Nadine, for answering those questions, but that is all we have time for today. So all that's left is to thank Nadine once more for a great presentation, and thank you to you, our audience, for listening. We hope you'll join us again soon.